So let me just get this started and then off to you, David.
All right, so hopefully this example, as you go through today, we'll go over some functions and some tricks we can do with ASPEN, and it'll save you a lot of time for project one. I know in my announcement I said that we will be doing separation of water and ethanol, but I forgot that pressure swing is not possible with ethanol, so I switched it to THF, and THF stands for tetrahydrofuran. So to get right into it, I know you guys already have experience with ASPEN from the homework 1, so let's just open a blank simulation right away and input our components into the list into our list. So for well-known chemicals, you can just immediately input the name into this row, such as water, right? But something like tetrahydrofuran, THF, it can't be recognized by ASPEN. And you can notice that by the blanks of the component name and alias. So let's just go delete that and find tetrahydrofuran. And I'm going to be trying to move pretty quickly because I know it's not a good time to have a review session right now or a tutorial session right now. So stop me if you have any questions or if you want me to repeat anything that I said.
And the video will be posted later if you need to review it.
And a lot of these components have some weird naming. When you have a lot of components, it can be hard to keep track of what means which one refers to specific components. So it is convenient to rename these to however you want to. So rename that. And for this example, we will not be dealing with hydrogen, but you will be dealing with hydrogen in the project. So I just wanted to show you how to configure Henry components into a simulation. And we will use pentane, and I can't believe it doesn't recognize that. Yeah. Pentane and decane for a very quick example later on.
And you can also just put the empirical molecular formula into that Finder box and search from there too. So you don't have to actually know the name, just kind of know C2H6 or something like that.
Yeah. So up to this point, everyone's familiar with. We finished inputting the components. Now, the shortcut key F4, the function key, will be your best friend if you're not familiar with ASPEN. It's the shortcut key for next, as you can see right here. Now, what next will do is lead you to the next interface page where you need to input, where you need to specify inputs. For anything that you do, if there are still degrees of freedom where it can't run the simulation, click F4 and it will specify what you have left out and what you need to put in to run the simulation. So when we click F4, it leads us to the thermodynamic package, and like I said, similar to the project, we'll be using the NRTL. It's a non-random two-liquid activity coefficient model, and it's reliable for almost any system. Now here, it's important that we configure Henry components into our thermodynamics because hydrogen is a non-condensable gas like oxygen and nitrogen. We must specify that it is a Henry component or else it will mess up the thermodynamics when you run the simulation. It will treat it as if it's a condensable gas and it will have some weird binary interactions with liquids. So just click on new here and the naming really doesn't matter. Now when you input that Henry components, we haven't specified which components in our list is a Henry component. So you can see here this folder, let me expand this out. Henry components folder, you can see that it's red and its input is incomplete. So let's edit this here and drag hydrogen into the selected components. Okay, now F4 is your best friend, just keep pressing F4. Now it's calculating the binary interaction terms. It did so for NRTL. And this is how you can ask ASPEN to estimate missing parameters by using UNIFAC. There are ways to estimate parameters using regression of empirical databases, but that's outside the scope of this project. So we'll click that, click F4 again, and you can see that properties input is complete, and it's asking us if if it should run the property analysis setup. You can also tell whether you're in Properties tab or Simulation tab that all inputs are complete by this text down here on the bottom left corner. So let's run it, and the run shortcut key is F5. This F5 will be more convenient to you than running with F4 because F4, after you run it with F4, it will take you to the control panel results page. Sometimes it's just a waste of time, and you're going to have to go back to your results, whatever you're looking at. So instead, you can just click F5, and it will run without interrupting whichever interface page you are in. So here we're done with modeling the thermodynamics of our components list. Now, there's a lot of things you can do here before you even move on to the simulations. For example, if we want to look at the pure component properties of our of tetrahydrofuran and water, we can click on this pure button here, and it will give you a list of property types, whether it's thermodynamic or transport, whether you're investigating viscosity, something like that, or mostly, for design classes, we'll be looking at thermodynamic properties. So let's say we want to see the vapor pressures of tetrahydrofuran and water to calculate their relative volatilities. So PL is the vapor pressure for a pure component, and we can select that here, and whichever units you would like. And it will calculate whichever property you want to see within a range of specified temperatures. And the default is 0 to 100. Now we just select the components that we want to investigate with the property method of NRTL and just run our analysis. Now here you can see that the green line is the vapor pressure of THF, and the blue line is the vapor pressure of water. So based on this diagram, which one do you think is the lighter component? THF, right. A higher vapor pressure corresponds to a lower boiling point, right? Antoine's equation. So this pure investigation here, it makes Googling almost useless. Whether you want to see how density relates as a function of temperature or any property that you would like, you don't have to Google for tables anymore. You can use ASPEN to generate every parameter that you can think of. In this case, for our project specifically, vapor pressure is useful because it provides a basis of how the relative volatilities of the components. It gives you a basis of where to split first and how to design your sequence of distillation. Okay. Now, what's even more important than pure component analysis is the binary analysis, and we'll come back to that once we've modeled our distillation column. Okay. So now we'll move on to the simulation tab, just like you have done with homework 1 to configure the reactor and the flash. Now, as I said before, we'll do a pressure swing distillation with tetrahydrofuran. So for a distillation column, we will specifically use rad-frac block, the rad-frac block in ASPEN. I think it is the most rigorous calculations for distillation, and it is the most reliable. So we put our block down. I just like to turn off 3D icons. I just think it's cleaner this way. It actually looks like a PFD that you might see in industry, or it looks like the ones you've seen in your internships or co-ops or whatnot. Here, let's call this column 1 and add our streams. So for the rad-frac block, you can see that the red arrows are the required inputs. So we need a feed stream going into the column. We need a bottoms product, and we need a top product. Now, this arrow here corresponds to a vapor distillate product versus a liquid distillate product. Theoretically, their compositions should be identical. It's just a matter of the condenser will have to work harder to condense all of the vapor overflow to get a pure liquid product. So let's just say we want a liquid product. I didn't specify in the project statement, but for this case, let's say we want a liquid product, so we'll have our product top stream labeled here. And I like to keep track of my stream tables, so I'm going to rename all of these to whatever I want to. Let's say this is distillation column 1 top stream, distillation column 1 bottom stream. And we can align the blocks for those who have OCD. Now, I haven't went over the problem statement here. For this example, our feed stream has 600 kilograms per hour of THF and 500 of water at 25 degrees C and 1 atmosphere. Our goal is to obtain a pure THF stream with 99% purity with at least 95% recovery. Now, THF in water, THF is so volatile that it might be easy to obtain 99% purity, but you can, we'll see that because of the azeotrope, it's impossible to obtain that purity with a single distillation column. So let's configure our feed stream. Again, if you don't know where to go from here, or any point of your simulation, just always click F4. It will always direct you to incomplete inputs. So it directed us to the feed stream. And again, I said it's 25, 1 atmosphere. And you can either specify a total flow rate here and fill in the composition here. This composition table does not have to add up to 1. It will simply just take the ratio of this total. So you could have done 5 and 6, and it would have been the same composition. Another way is just delete that total and configure it directly into here. So it inputs both the flow rates and the fractions at the same time. Okay? So you can see that the feed stream input is complete, and again, our best friend, F4. Now, it's leading us to our column 1 specs. This is the input page for a radfrac column. So in the problem statement, we have 20 stages for a typical radfrac column. Condenser here. Do you think it would be a total condenser or a partial vapor condenser? Looking at this flow sheet here, where our top stream is a liquid product, what do you think the condenser has to be? Total, right? Now, if we try to put a partial condenser instead, ASPEN automatically tells you that there is an error inconsistency, that you're not matching inputs for me, and it's having problems. So we'll switch that to total, and you don't need to touch any of these. Anything that's default here, usually you don't need to touch. Okay. Now we have 2 more degrees of freedom left. 2 of distillate, blah, blah, reflux ratios, distillate bottom feed ratios must be specified. So we have 2 degrees of freedom left on this page, and you may specify any of the 2 from this drop-down list. But I guarantee you, and I know Jared will agree with me on this too, the easiest 2 variables to manipulate, this is very important for a radfrac, is to adjust the reflux ratio and a product stream flow rate. Okay? There's no need to manipulate the duty of the condenser, the reboiler duty. We don't know how to calculate that really on paper. Unless we have a very specified duty and we want to see how that affects the performance, we will always ask to obtain a certain amount of product, and ASPEN will calculate the duty required to make that happen. So again, reflux ratio is already chosen here. So let's just go with 3 for now. And what's left is 1 of the product flow rates. What I like to do is either a distillate to feed ratio or a bottoms to feed ratio. You may also specifically put distillate rates and bottoms rate, but these, so these are, let's say, the distillate rate, if you specify it in this way, ASPEN will run this column calculations to make sure you have a distillate product flow rate of 200 kilograms per hour. But if your feed stream changes at all, let's say it's a column downstream and all of a sudden you're doubled in the feed stream, and you want, now this number here may not reflect the operation that you want. So instead you may choose distillate to feed ratio. Because it's a ratio, no matter what the amount of feed is, it will always produce that ratio of product on the top stream. Okay. So for the first column, we'll do distillate to feed ratio. So here it's kind of a guess and check game for now. So theoretically, if we want to have a pure stream of the lighter component, THF, we have 600 kilograms an hour on the top stream and 500 kilograms of water on the bottom stream, right? So theoretically, the distillate to feed ratio should be 600 divided by 1100. So let's see if that works. So it's around 0.55. I didn't do that in my head. I already had that calculated. Okay, so now all of our inputs are complete for this configuration, and just keep moving on to wherever you see red. So to streams, this is inputting the feed location on the column. You may have learned from separations class, McCabe-Thiele analysis. The feed stage location does matter, but it is almost insignificant compared to your reflux ratios and product flow rates. So what I like to do as a base case, I just put it right in the middle of the column. So because we have 20 stages, I'm just going to say, hey, the feed's coming in at stage 10. Okay, on stage, above stage, it really doesn't matter. Okay. Now pressure, let's try 1 atmosphere. To save duty, the feed stream's coming in at 1 atmosphere, and we will operate the column at 1 atmosphere. Okay. So you can see now the required input is complete on the bottom left. We can run the simulation. You can press F4 or F5, and like I said before, F5 is definitely the more convenient way to run a simulation. So if you click F5, boom, it has a simulation error. Now, the source of errors on ASPEN there's hundreds of sources of errors, but in our case, it means that to obtain 55% of the feed flow rate to the distillate at a reflux ratio of 3, it is physically impossible. Okay? And you can see that from the results tab of column 1 on the left. If you go to results and click on status, you can see that the block column 1 is not in mass balance. Okay?
The other way you can get to that error is at the check status button on the left. So if you kind of like exit out of everything, that will list all the blocks that have errors that you can kind of just go through and pass.
Just one little trick before I move on. We can increase the number of iterations ASPEN does for the simulation. And the default iteration max is 25, and we can go up to 200. So just in case, I'm going to increase that to 150, let's say. Or maybe, 200. Okay? Maybe it was that there just wasn't enough iteration to converge the mass balance. So what I'm going to do is I'm going to reset the simulation right here. This is incredibly important, especially with distillation columns. This resets your simulation results, and it will run as if it's your first time running it. If I were to run the simulation again, it will use the results of your previous run as the first guess of the iteration of the next run. And it can cause a lot of problems with your results. It might not even run the simulation as well. So always, yeah.
It'll give you false results because you'll run it.
Yeah.
And because you haven't reset it, you think it's great, but then once you reset it back to square one, and then you run it again, it'll error out, and you're like, oh, I thought it was so good, and it worked, and you're screwed.
So I had no idea that the screen wasn't down.
Reset is key to, when you change inputs in your column or anything like that.
Yeah. So the shortcut for reset is Shift F5. Just click OK, click OK. You can see that all of the results have been purged, and click Run again. Sorry. And we're still getting an error. So it's not an iteration issue, it's your specifications. Because if I input a distillate to feed ratio of 0.55, where all of that tetrahydrofuran is going to that distillate stream, it's physically impossible to achieve 100% purity of that distillation stream. Okay? And as you guys might already know, based on the hint of pressure swing distillation, there is an azeotrope between THF and water, and that's why getting a pure stream with one column is impossible. And ASPEN will tell you that. It won't tell you directly, but you might have to use your logic, use your understanding of certain unit operations to know that that's what's causing the error. Okay, so let's just try different numbers. Let's try 58%, and reset, and run. Right, so 58% works. Now you're going to see that, especially with radfrag, it's very tricky because these input parameters have a range of feasible values. Okay, so 58% worked. Now let's just try, let's say 40%. And that also worked as well. So instead of playing the guess and check trial and error of these input specifications, we can use sensitivity to save your time. And I think Stephen, or my section's homework TA went over sensitivity with our class at least. I'm not sure if. Okay. Okay. So sensitivity allows us to vary parameters for us. It's kind of like the for loop in MATLAB, right? So to go to sensitivity, just click this button on top on the home page, and we're going to create a new sensitivity. You can name it column 1. And what we want to see, what we want to see is how does varying the distillate product flow rate, how does that affect our results, and which ones are viable and which ones are not. So when you create a new sensitivity page, you'll be prompted to this interface here, where you'll see that on the top there's a vary tab, define tab, and a tabulate tab. Treat vary as your independent variable, right? It's the x-axis on a graph, and you are defining the dependent variables that you want to see. So it's your y-axis. So in this case, we want to see how this number here, this 40% distillate to feed ratio, affects the purity of THF on the top stream and its recovery, right? So if we go back to the sensitivity, we can create the independent variable by clicking new and just follow these drop-down menus here. So because we are manipulating an operations spec of a block, right? These are blocks and these are streams here on ASPEN. All of these are blocks. So we're manipulating the ratio of a block, so it's a block variable here. And which block? Column 1. We only have one block for now. And the variable that we want to manipulate is the distillate to feed ratio on a mass basis. So we go down to mass and click on D:(F). Okay. And we can change from, let's see, from 10% to 90%, and let's give it an increment of 1%. Okay. So it's going to run this simulation 81 times and give you the results that you want, whichever variable that you want to define. So we want to see the purity of THF and the recovery of THF on that top stream. Recovery we can't directly calculate, but we can see it's just a number divided by 600, right? So purity here, now we're looking at the top stream here. So our input is now a stream variable, and the mass fraction in the distillate stream of THF. And recovery is just the mass flow in the distillate stream of THF. Okay, so now we're done here. And with the tabulate tab, we can just fill variables. Easy as that. Okay, now once this is done, we run the simulation again. And it's going to give you an error because certain cases of your sensitivity was not feasible. Okay, just like how we saw that with 55%, it caused an error, whereas certain values worked. If one case of the sensitivity fails, then it will give you an error message. So here, let's ignore that for now. And the results of that sensitivity is tabulated here. But you can easily make a graph from ASPEN here. Okay, so let me do that again. So once you run it, there's a results curve right here. And just click OK. And you can see that by varying the ratio, it changes both the purity and the recovery. The most important thing to learn from this graph is that purity and recovery are trade-offs. You can never increase recovery and purity at the same time. Well, maybe that's too extreme to say, but usually, in 99% of the cases, purity and recovery are trade-offs. If you want to increase your purity of a stream, you will have to sacrifice recovery and you will lose product. Okay? So, let's say our optimal point is the intersection here, where it seems that both purity and recovery are pretty high, right? So that corresponds to a value around 58%, let's say. And we can be more specific with this tabulated result. But it seems that this point here is good enough. And something like this can be your justification on the report. Why you chose this value? Well, look at this graph. And I subjectively determined that this is good enough. This is what I want to go for. Okay? So 58%. I'm going to deactivate this.
I think David and I both, we're going to like to see these graphs and these curves for your justification, so that we know that you know what you're doing.
Yeah. So I'm going to run this again with 58%. One more thing is by default, ASPEN is, the report options, it's not really good. So it will only give you the molar flow rates by default if you open ASPEN. So go to Setup and Report Options and the Stream tab to click on Mass Flow and Mass Fraction. And in your stream tables now, these will appear. Okay, so if we look at the results of the column, we have the bottom stream and our distillate stream. And I like to use the format kcho.chbe. And there we go. So in our top stream, we have 600 kilograms an hour of THF. That's 100% recovery. But it contains a small amount of water, right? 94%, so that's the mass flow here. And you can see that the mass frac of that distillate stream is 94%, right? And that's not good enough for our objectives. So you'll see that, well, I don't want to get too much into this, but increasing this purity by more than 95% is impossible because of the existing azeotrope. And I know that I uploaded the azeotrope finder on ASPEN, but because we already know that an azeotrope, because I'm telling you that there is one, and we know that there is an azeotrope, we don't need to necessarily go into the finder, but develop a YX diagram that's much more useful for us. Okay. Do you guys remember YX diagrams from separations, McCabe-Deelys? Okay. So to do that, we go back to the Properties tab, and we want to see how THF and water interact, and this binary button here is what we want to click on. So it'll prompt you to a TXY diagram page, and from this results, we can develop a YX diagram here. So water is our input, a component of interest in THF. We want to see everything in terms of mass fraction, and everything here is ready to go already. So we want to see the binary interaction between THF and water. And the result is a TXY diagram, and you can see that the azeotrope is right there at 5% water. So let's switch this to THF. 95%. Oh, sorry. I should have explained. So once we run that analysis, this plot window will pop up, and just go down and click on the YX diagram. Okay. So here, what is an azeotrope? It's the point where the vapor fraction of a component equals that of the liquid, right? And separation beyond that point is impossible with just simple distillation, right? So if we input a feed 55% THF right here, the distillate stream will produce up to 95%, and it cannot pass that point. It's physically impossible, right? Let's see. So, okay. So this is where pressure swing distillation comes in handy. This azeotrope point is very sensitive to pressure of that stream. So we can develop this YX diagram again with varying pressures. So go back to the input of the binary page, and we can list the pressures that we want to evaluate our azeotropes. So let's try a vacuum pressure, atmospheric, and high pressure. And we're going to run this again. and go back to input and generate our YX diagram. Okay, so you can see how these curves are varying with pressure, and if we zoom in on the top right corner, you can see that these azeotrope points decrease with increasing pressure. So the blue line is the vacuum, the green is the atmospheric, and pink is the 15 atmosphere. And you can see that these azeotrope points where it intersects with the with the dashed line, it decreases as you increase pressure. So I think it's important to see what's actually going on here, like on paper, before we move on to the simulation. So we zoom back out. So currently our first column is operating at 1 atmosphere, right? And we have a distillate stream, and we have a bottom stream, and this is 94% pHF that we got from our last run, whereas this is pure water, or mostly water. Now, based on this YX diagram, at 1 atmosphere, we're feeding into our column around 55% THF. So our feed is right here, right? So the distillation column will produce 2 product streams, one going this way and one going that way, right? And theoretically, the max separation is that azeotrope point and the one at the bottom left corner. So our distillate product will be at that azeotrope point because we can't pass that. If we have a reflux ratio at infinity, we will achieve right at that point, right? So that's going to be our distillate. And this will be our bottoms here. Oh, that is not the right word. It's okay. No, it's okay. It's okay.
We'll clean it up later.
It's okay.
Just don't tell.
Right.
At least you didn't do Sharpie on the screen.
Yeah, that's right. Now, with this distillate stream, what are we going to do with this in a pressure swing? We're going to increase its pressure to, let's say, 15 atmosphere, and feed it to a second column to produce a bottoms and a top again, right? Now here, what's interesting is, now our distillate stream here, I drew this wrong. 1 atmosphere, so it's around there. So 94% was right here. That's our distillate stream coming out from that first column. It is now our feed stream to the second column, right? This is our feed, and it will again generate 2 product streams moving away from this feed point. Okay, so it will produce 1 stream at this point, the new azeotrope at 15 atmospheres, and another at 100% purity of THF. Okay, you guys remember this from separations? Right. So this is how pressure swing distillation works. We are, from that first column, we approach the azeotropic point, and we swing the azeotrope down by increasing pressure, right? And then we have another separation here. Now in this case, because the YX diagram is now underneath this dashed line, THF is in this part of the right side of the azeotrope. THF is the heavier component, whereas the water is the lighter component. And we'll see that in the simulation. Okay. So based on this analysis alone, we can determine that our first column will operate at 1 atmosphere and our second column will be at 15. Okay, let's just try that out. And things like this, the YX diagram and just the procedure that I just went through is good justification of how you designed your process. Okay, we like to see figures, 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 figures. So back to our simulation tab. Okay. Whoa. So let's replicate what I have on the board. We want to increase, where is it? The distillate pressure to 15 atmospheres and feed it to a second column. Okay. Reconnect.
Just a quick comment, if you chose to do the vapor distillate, then you would need a compressor instead of the pump. So if you know you're gonna do PSD, it's kinda better to just do a liquid distillate, so then it's really easy on the pump to get it into the second column.
Okay. So there's our second column. Here's our pump. And let me race through this. Discharge pressure of 15 atmosphere. (20 stages for the second column. We have another liquid product stream, so total condenser, distillate rate mass. Okay. And let's just see reflux ratio of 5. And distillate rate, I've already ran the sensitivity on this just to save time, and I found that 230 is optimal here. So, right, and then streams, let's just feed it to the center of the column, right in the middle, and pressure, very important, at 15 atmosphere, okay? So this is what our PFD looks like as of now. So D, let's say this is column 2 feed, D to bottom stream, and D to top stream, okay? And let's pray to God and that this works and run the simulation. An error.
Yeah, and Dave's really quick at it, but just remember he's doing reset and then run. So what was reset again? F6?
Shift F5.
Shift F5 and then F5, right?
Oh, that's right.
I tend to just use the buttons just because I'm a little slower with stuff.
Okay. Oh, there. Now it worked. Okay. Now, let's see what happens here. So in our first column, our distillate again has 100% recovery, 94% purity, and it is increased in to pressure, and it fed to the second column. And in our second column, this is the distillate stream, and this is the bottom stream. So in our top stream, or in our bottom stream is now the stream of interest, right? As we've seen on the YX diagram, at the right side of the azeotrope, THF is the heavier component. So you can see here, we have 403 kilograms an hour of THF, it's terrible recovery, right, 66%, and 99.1% purity. So by doing this pressure swing distillation, we broke the azeotrope point and we got to our objective of 99% purity. But we're sacrificing recovery for this. So the solution to this, the real complete schematic for a pressure swing distillation, is to recover the lost stream by recycling it to the first column, okay? Now, I'm not gonna add it in here, but remember that our second column is at 15 and it's at 1 here. So theoretically, you do need some sort of pressure reducer in this recycle stream to go back to 1 atmosphere, okay? Now that we added that recycle stream, let's call this recycle. So our first column will have pure water, and the bottom's product of our second column will have THF, right? This is our product stream that we want with 99% purity and 95% recovery. Now, we added another feed stream into the first column, so it's asking where do you want to put in that second feed stream. And, you know, calculations, optimal point on this is beyond me. I don't want to spend time on it. So let's just put it right in the middle again, okay?
You can feed as many streams as you want into a column, but you also then have to specify where they're going to go, what stage they're going to go to.
So luckily, it converged. Recycle streams are very problematic for ASPEN sometimes, but I think we got lucky. So if we look at the bottom stream again this time, now we have 99.3% THF with a recovery much better than before, right? So 537 kilograms of THF, that's 89.5% recovery. It's still not enough to meet our objectives, right? So there are a lot of things to tweak here. What can we do? One, we can increase the delta P of these two columns, right? We can operate this at vacuum and we can operate this at 20 atmosphere. But that could be very expensive to do, right? Our duty is going to skyrocket. Another one, increase stages, increase reflux ratios of both columns, make both columns work harder for better separation. But usually it takes minor tweaking before you get to that. And I've taken the time to investigate. So I'm just going to tell you that 61% for the first column is going to improve our recovery. So you're going to have to play around with this to get an optimal point.
And so much of the simulation is going to be trial and error of whatever you're doing. So just plug in a number. If it doesn't work, kind of think about why, put in a different one, and keep going from there.
Come on.
What do you have? That's, yeah, there you go. Just gonna error out.
Yeah.
Did you change the iterations on the second column to be was 202?
Mm-hmm. ASPEN is definitely frustrating at times.
The other thing is sometimes it's weird because VLab Aspen will be a little bit different than on the computers downstairs. I trust the computers a little bit more. It's still the same thing, but we've just found some unexplainable troubles.
If you notice what I did, with each specification, I changed it by very, very little. It's just how the first guess of the first iteration interacts with just the next run. It's just trial and error. Sometimes it will give you an error, although it really is feasible, and you just have to be patient. Okay. So after investigating what I can do, I changed the distillate ratio to 61%. And in our THF product stream, we have 99% purity and 95.9% recovery right here. So that's how pressure swing distillation works. And with your components in the project, there will be quite a few azeotropes. And some procedures like this can help you kind of take a step back and you can decide what to do first. Are you going to treat the benzene azeotrope first, the toluene azeotrope first, and things like that. Okay. Now, for the part 2 of the project, let me do this just really quickly. Energy is now integrated into the problem statement. Okay. So I'm just going to give you a quick example with the flash column to see how increasing purity and recovery interacts with energy, and how you want to choose an optimization strategy for your project. Yeah?
Can you tell me again why you used the pump?
So because it's a pressure swing distillation, and the first column is operating at 1 ATM and the second column is at 15 ATM, you have to increase the pressure of the stream before going into that second column, because you can't feed in a 1 ATM stream to a 15 ATM column. Pressure differential would not allow that stream to even go into the column.
Right. So in real life, if you have the second column operating at 15 atmospheres, it will backflow, right? Flow always goes from the higher pressure to the lower pressure. ASPEN will still calculate that for you. It's very theoretical, but it'll just give you a simple warning. But for feasibility's sake, on your report, any change in pressure, you should indicate that specifically with a pump or a compressor. Never input a stream of 1 atmosphere into a 5 atmosphere block. You know what I'm saying? How did that 5 ATM even, where did that come from? Where did that pressure, that compression come from, right? Aspen will do that calculation because once it goes into as 1 ATM and at the block it reaches 5 ATM, it will overwrite that pressure that was coming into, right? So it magically will have 5 ATM. But in real life, that's not the case, right? So this is just to reflect a more realistic operation. Aspen will run it without this pump. Okay.
And just another clarification for the project. So we only specify when you're doing a differential pressure that you'll need a pump or compressor or something. Transfer lines don't matter. So if both of those columns were 1 ATM, you don't have to put a pump or anything like that.
Yeah.
So Aspen will do that. In real life, of course, you will have pressure loss, but we don't deal with that here in the simulations.
I know this tutorial is going to go long, and let me just race through this real quickly, and then I'll probably upload this Aspen file to you guys so you can take a look at this again. Let's just quickly look into energy and how that plays with the degree of separation that you want to do. So in a quick example, a flash drum here. Let's say we have a stream of 50% pentane in decane. I'm just trying to be quick here. Let's say we have 1,000. Okay. And mass
Fraction,
fraction.
you
Yeah.
do 0.5.
What's that?
You did 1 to 1. So
Yeah, yeah, 50.
0.5.
Oh,
Because you did mass fraction.
yeah. Well, the compositions don't have to add up to 1.
Okay.
Yeah. So I could have done that, and they would still be 50-50. So let's see if we run this now. We're just looking at pentane and decane, and we want to flash off the lighter component, pentane, to make a pure bottoms stream of decane. Okay, so here we're going to flash off the pentane, and we're going to leave decane down here. So in our results, you can see that nothing is being flashed off right now because the flash is not hot enough. So again, instead of guessing and checking, you can immediately go to sensitivity, add a new sensitivity for, let's say, the flash. And now we can vary the flash column's pressure. Let's say, oh, sorry. Why did it click pressure? Temperature. From, let's say 30 to 100. Now, you can also nest independent variables. So you have, a for loop within a for loop. Let's try that out with pressure of the column. So we're going to vary both temperature and pressure. It's very similar to your homework, right? Let's say we want to do at vacuum 1 and 1.5 atmospheres. Okay. And we want to define the purity of decane in the bottom stream, the recovery of decane, but also now, more importantly, the duty of that flash column. So let me do this really quickly. Now, for the duty, we want to see the energy consumed by that flash column. So it's a block variable, flash, and we have, this is a trap. Duty here is a specific input duty. You can specify the duty for that flash column. Instead, you want to see what the duty is calculated by the simulation. So you're going to click on kcho, calculated heat duty. in whatever units you would like. Tabulate, and let's run this. So, with varying both the temperature and pressure, you can see on the x-axis we're varying the temperature of that flash column, and as you increase the temperature, you're removing more pentane, right? So the purity of the decane in the bottom stream increases. Now with pressure, this is a vacuum pressure. The lower the pressure, you need lower temperature to flash off that same amount, right? Higher pressure, you need more the boiling points go up. So you can see that with decreasing pressure, you can get even better purity at lower temperature. Okay, now looking at recovery. So the trade-off, right, between purity and recovery is shown here. Before, when we increased the temperature of the flash, we got better purity of decane. But as you increase that temperature, more of that decane is going into that top stream, and we have lower recovery now. We're losing decane more in that top stream. And let's look at duty here. As you increase temperature, you need more heat supplied to that flash, and we have increasing duty at various temperatures and pressures. So this is the results of the nested sensitivity. And if you want to manipulate that data or plot it in different ways, you can copy this to Excel and do whatever you want with it. Now, one final thing. No.
Cool design right there.
Okay, so let's digest this graph just a bit. So in our results, with higher temperature of the flash, we have better purity of decane in the bottom stream with worse recovery. So you can also see that the duty is increasing with increasing temperature. Right, so there's several things you have to think about. The degree of separation, the amount of product lost, and the duty here. And with this graph, you can make a subjective call. The project statement is vague on purpose. We're not asking for a specific strategy. It's up to you. If you want to obtain the highest purity possible, while still using, if you believe that supplying a lot of heat to that flash column is worth it, it's valuable, then do it, right? The project statement currently says that you have to minimize energy consumption. But if it is deemed necessary, then it's your call, right? So plots like this gives you a very good idea of how you can approach the part 2 of the project. And when you justify your choices, show that with these figures. Show that, oh, I just wanted to go with the intersection. I'm going to weigh duty and degree of separation half and half. I want to consider them equally important. So I will just chose a point here, or I want to minimize product loss. So I'm going to bring it way over here. You know, the purity is not going to be that good, but I have more downstream separation units, so this is going to be okay. Things like that, okay? So it's completely up to you. Just be confident in your judgment and decision and justify it, okay? It's not, you know, Design 1 course isn't really like your classes before where there is a right answer. You can do whatever you would like as long as you justify and it's feasible. If it's completely wrong, it's very obvious that it's completely wrong. But most of the case, if you're confident and you know so based on your knowledge and evidence, then it's totally up to you, okay? So, you want to start recording?
So, yeah.
So I know I kind of flew by some of these things, and